Yep. Good afternoon, everyone. So my name is Charan, and I currently work as a senior analyst in Flutura Business Solutions. And it's been about 4 years for me here, and started off as a domain consultant. So the background that I come from is petroleum engineering. So I did my graduation in PES with a degree of applied petroleum engineering with specialization in upstream. Then joined as a domain consultant, then moved on to the pre-sales side, and now kind of the strategic part of itself. So first of all, I would like to thank Advantage for asking me to present something from my experience itself. So predictive maintenance, especially across the oil and gas value chain, is something that I have been working on for about 3 years now, where I have observed various trends which has been the kind of requirements for the the industry to sustain. So just sharing my thoughts here, and I've put a few slides also which can help me across this session itself. So I am not sure about the discipline of the participants, of what disciplines they are joining. So what I'll do is I'll just try to keep it at a very macro level, very general level. But if you want, you can ping the questions probably in the chat box, or you can connect with me later if you have any doubts, and we can take it up. But in between, I'll take pauses also, so that if there are any questions, feel free to ask it, or towards the end also we can keep it. So yeah, anything before I start? Any expectations, or shall we directly?
Yes, sir. We'll directly start with the presentation.
Okay, sure. I'll stop the video for now and start sharing the screen. Let me know once you can see it.
I can see the presentation.
Perfect. Okay. Yeah. Let me start off with the very basic question, right? So, what is predictive maintenance? Why is predictive maintenance a key requirement in today's world? So, I'll just take an example of the oil and gas industry per se. So, I'll be taking up examples across this particular industry itself throughout the session. So, for example, if I am a plant operator, okay, and I'm managing a gathering network in US, for example. So gathering network is a combination of wellheads and well pads. So well pad is a combination of different wells at the same location. So wellheads, well pads, and compressor station, dehydrators, separators. Then you have your gathering pipelines also throughout the network. So the scale that I'm talking about here is about 300 plus well pads, then 20 or 25 plus compressor stations, which sums up to about 50 or 60 plus compressors, the same number of dehydrators, separators, and miles and miles of pipelines spread across. So the key question, or the key the problem that is faced by the plant operator here, or you can say area manager, is which equipment should I check first, or how shall I maintain the operability or the utilization of the equipment across the network. Okay, because if I want to intervene and go ahead and analyze which equipment is actually causing me an issue. So the issue can be if you're talking about pipelines, it can be blocking of the pipelines due to accumulation of hydrates or wax deposition. If you're talking about compressors, it may be any hot valves which are there, or if you're talking about separators, then there is some coagulation which is happening. Or if it's a simple pump, then it can be overutilization or underutilization, which might lead to wear and tear of the pump. So all these identification of the events requires a kind of a manual process of understanding which parameter should I look into. Then I'll go ahead and analyze the trends, how it has been. And based on the OEM's documents like specification sheets, troubleshooting guide, and based on the experience. So if I'm a 10 plus or 20 plus years experience in the field, then I'll know in the back of the hand, okay, this is the event, or this is the probable event which might be occurring here, which might be leading to failure, which in turn impacts the sales of the natural gas at the sales point itself. Okay. But what if I'm a newbie? Okay, I'm very pretty much new to the field. I have a previous experience, but I'm new to the field, so I won't know which equipment should I look out to first. What are the different workflows, because each operators have a different kind of workflows to adhere to these inspections, you can say, in a nutshell. So this is kind of a manual process which can take from about a few hours, even a whole half a day or a day, just to understand if all the equipment are working fine or. And if I get to know, okay, there is some issue, then either I'll send out a reliability team over there just to check out, okay, what might be the reason, just go ahead and check that out. Or if I'm a process engineer, then I'll have to simulate different scenarios as well. Like if I want to change the compressor, or if I want to do a maintenance of the compressor, shut that down. So first I have to do a kind of a simulation just to understand what should be the optimal set points or the redirection of that natural gas across the field, so that I can go ahead, intervene, and bring back the network to the norm. So these things or these activities takes time. It takes about hours to do that. So this kind of a reactive nature of adhering to the event. So after that event has happened, or at the very worst, we'll get to know, okay, we have to go ahead and intervene, which might lead to some downtime or production deferment. In case of drilling, it might lead to npt of few hours. So since drilling is a very a short duration based job, which lasts from about 7 days to even 20-25 days, not more than that. So each hour counts there. So each hour or each day can cost millions to the contractor. So being reactive in nature, the traditional approach is something that every operator or a contractor is looking to change. So that's where this term of predictive maintenance coined in. So in the beginning, it was very difficult to address this problem and bring out the solution, because I can share one example from my side. So I went to EDPEC in 2019, where I was interacting with various operators in the Middle East. Okay, so the primary question was, how will you solve it? So like we had few use cases, proven use cases, where we talked about predictive maintenance, optimization, gathering system optimization, etc. So the primary question was, are you sure if you can do it? So that confidence on the predictive in nature, or you can say artificial intelligence altogether, it's still a very nascent stage, I'll say, for this particular industry. There are big players like Shell, Chevron, even BJ services, or if you talk about the contractors, even the OEMs like Keppel, right? So uh, they have gone ahead and invested a lot of money, because they have understood, okay, this can be a game changer for them. But for a few other operators, it's still a kind of exploration phase that they are into. So that's the kind of I'll say 30% agreement, 70% still they are figuring it out, okay, what to do, how to do. Because for some people, predictive maintenance or even that AI means just a visualization, because in the digitalization journey for any of the operator or the contractor, it begins with collection of the data, then analyzing the data, then bringing out insights, and then notifying the user. So these are the key steps when it comes up to there. So for them, even the real-time monitoring itself is a crucial aspect. Then slowly building on top of that, you can go ahead with the diagnostics, more in terms of anomaly detection, and then the prediction, or you can say the autonomous prediction of the equipment, which brings back the whole chain and completes the cycle. So that's the final stage that any operator or a contractor wants to go ahead with. So that's where this particular thing called predictive maintenance coined in. So it's like predicting when the maintenance is to be scheduled for a particular equipment. So based on the few critical KPIs that is being calculated for each of the equipment, whether it be a top drive in drilling, pumps in the production field, compressors in the midstream phase, or even the crude distillation column or the heat exchanger in the downstream refineries or processing plants. So there has to be key KPIs or the derived parameters which have to be understood, based on which those variations can be put into account in terms of a kind of a health score or kind of a degradation score. These are few terms which which is the end KPI through which we understand, okay, if the health of an equipment is going down, then that means it has to be intervened. So based on that, we can sort different equipments and go ahead and intervene. So this is how predictive maintenance helps the reliability engineers to prioritize which equipment that they should go ahead and intervene as of now, which will reduce the impact across the field or across the plant, and to make sure that the smooth the operations or the processes are running smooth across. So this is how I wanted to kick off this particular conversation. Now, talking about the predictive maintenance as a whole, so there are a few questions that I've tried to map it here, like is the equipment is working fine? If not, then what is the issue which is actually causing this equipment to work outside the optimal range? Or how shall I increase the visibility to pinpoint the kind of an what is the various symptoms leading to the event, or what we call it as an RCA, root cause analysis. So how to do that? So these are certain questions which are raised in the minds of the engineers, because towards the end, any downtime experienced across any unit of the refinery or even the small area in the field, that will impact the overall production or the yield or the throughput of the whole field or the plant itself, which can be causing either a kind of monetary loss for the customer who is buying that particular natural gas or any of the fluids from the operator. So that is first thing. Second thing is, if you're a contractor, right? So you should be adhering to the different timelines which have been provided by the operator. So if they have given you 30 days time, in that itself, you have to set up the whole rig or the derrick, and then get the drilling process started, operation started. And you have to finish that off, whatever the measured depth, whatever the different KPIs that you have to achieve, and take your all the equipments out. So that's how you maintain your repo across the operators. But if you're not able to adhere to that, that might cost you in terms of any penalties, or even the relationship with the operators. Because if you're managing 200, 300 plus rigs, it becomes very important that you are able to grab the various drilling contracts across these operators to make your organization grow. So these are the primary motivators for the service providers or the operators to go ahead for the predictive maintenance. And like I said, the traction in the market is now everybody wants to explore and see what can be the different possibilities that can be there for a very large scale of operations across upstream, midstream, downstream. So I'd like to cover that part as well in this conversation, just to make sure that everybody is aware of what are the different aspects of the oil and gas value chain itself. And so how does it work? Okay, so in a very broad way, I just want to say, as in, if there is a a production line in the refinery itself, or like I said, an operation in the field itself. So data is collected across all these equipment or the processes. So what do I mean by the data? So there can be various types of data which can be captured across these equipment or the processes. For example, there can be a time series based data. So what do I mean by time series data is for each particular time or a timestamp, a particular data is calculated, like or captured. For example, at 12 o'clock today, the data of the temperature sensor was 50 degree Fahrenheit. Then 12 o'clock and 1 minute, so 12:01, it was 51 degree Fahrenheit. So again, each timestamp, so the frequency can be at a second level, it can be at a minute level, hour level, or a day level. So against a particular timestamp, if you're capturing the data for any of the parameter, that is something which is called as a time series data. So that's a crucial aspect, because that shows the behavior of the equipment across these subsystems. Because over the time, the trends of these parameters change based on their operation. So if a particular equipment is trained, like if a compressor should run at the discharge pressure of 12,000 psi, but if it's being strained at 14,000 psi, that might reduce the operational time and it might require a maintenance a bit quicker. Or if continued, then that might lead to any damage or a failure event which might create a down. So that's the time series data. Next kind of data which comes into picture is the maintenance data. So what do I mean by the maintenance data is, so I'm pretty sure you must have been owning a car or a bike or any vehicle. So there is a certain amount of maintenance that you have to make sure that it does so that it's run smooth. Similarly, it goes for the equipment across this industry itself. So for example, if the compressor has to be, so the scheduled maintenance is about 8 months or 12 months or even 16 months. So at that maintenance event, there are various logs which is kept into place. Like if the valve was working fine in that, if the bearings are not damaged or if they are damaged. So all these logs are kept into place so that these logs can be utilized to analyze and verify the different signatures which are present for these parameters. So this comes as a maintenance logs. Third thing, it can be the user logs itself. So if there is a sudden increase in the temperature as an event which was noted by the reliability engineer, or if there is a leakage which was found across a drum in the refinery, right? So all these events are also logged by the users, as which is called as a user logs, which is also another kind of a data set which is used. And apart from this, there are a static information which is there, like specification sheets, like what is the rated parameter conditions which should be there. Like it should be operated between 10 to 12,000 psi for a compressor, and the flow rate of the pump that should be maintained at 700 gallons per minute, etc. So these are certain things which has been given by the OEM itself. So OEM means original equipment manufacturer, who is manufacturing this equipment. So they test it in the ideal scenarios and say, okay, this should be how the optimal set points that should be kept for the. So this information is called as specification sheets. And there are performance curves also which are available for these equipment. So what do performance curves means? For each of the correlated parameters, like total head against the flow rate for a pump, there should be a curve that it should follow. Okay. So this curve is particularly called as a performance curve, which varies across with the different diameters of the impeller diameters of the pump, or for the compressors, it may be the compression ratios, etc. So all this information sums up to be the performance curve for the equipment. So all these data gets utilized while preparing the ML algorithms or the machine learning algorithms, which is, you can say, a way in which artificial intelligence helps predicting the maintenance or any failures. Okay. So this data historian that you're saying, it's a kind of a time series based data which gets stored. This data store is basically, you can call it as a data lake, or a combination of all the data sources which are available for this equipment itself. These process flows can be the different workflows which has been created by the engineers itself. Like this should run for this much amount of a time, and this should be the optimal set point. So there are various workflows which have been kept by the engineers itself based on the experience. So this is another set of the information about that as well. So all these get stored in the data store. And what happens is, I'll tell you an example of how we do the process as well. So the data scientists who are handy persons or the go-to persons for the AI based or machine learning based algorithms. So what they do is they analyze the different parameters, and they just try to bring the correlations of how these parameters are impacting or giving out evidence that this event is going to happen. So how does that go off is, uh, you know, they read on the various historical tracks which have been happened over time. So in the maintenance logs or the failure logs, we will have that into account as in, okay, the failure event happened about 3 years back, where some kind of signatures was seen based on these parameters. So again, if that signatures appear again, then these models, these AI and predictive models or the ML models learn from that and predicts, okay, with the kind of a variation that was seen 3 years before, it's a kind of a similar behavior, so that failure event which was happening previously is kind of imminent now, with kind of a metric which we call as a probability. So it gives from a probability score between 0 to 1, saying, okay, if it's 0.7, it's a crucial, 0.9 it's like imminent, it's going to happen, 0.1, 0.2 means some behavior is seen but not sure, so we should go ahead and inspect. So this is how that models are built here. These algorithms are built based on these data stores or whatever information that is being captured for the equipment. Then either it can be visualized over the dashboard itself. So there are various providers who give kind of a visualization based dashboards, and another part is kind of a real-time alert. So nowadays, since more and more operators are moving towards the upper band of the digitalization cycle, so they have this handheld devices where they get a notification in real time. So any such event identification or the probability score which is breaching a particular threshold is seen, then in real time itself that alert is sent to that user. It can be through like I said, an handheld device, it can be through a message, it can be through an email, even the WhatsApp messages. So through that they will understand, okay, this equipment is facing certain issues. Either I should go ahead and intervene, or I should raise a ticket. So normally, like I said, in the control or the command center, if I'm a senior engineer or a plant operator or an area manager, I'll get an alert, and what I'll do is I'll raise a ticket for the reliability folks who are managing that particular area or the equipment, to go ahead and intervene and say, okay, boss, some failure related to the motor is identified by the algorithm. Just go ahead and inspect that motor as a subsystem itself. So inspecting the whole equipment also takes time, right? So if we get to know which subsystem to actually look into, that will help refine the whole process of inspection and reduce the time to action. So that's a kind of an alert which is generated and helps the engineers to go ahead and intervene. So this is in a nutshell how the predictive maintenance or the approach is taken for any of the equipment or the operation. So before I go ahead, any questions or any thoughts? Uh, this is over there. Hopefully you are able to hear me, right? It's not like I'm talking to myself. Confirm that. Hey folks, I am audible, right? And is my screen visible? Can anybody confirm? Okay, sure. Now, moving on to the next part, where I wanted to cover a bit about how does that oil and gas value chain works across. I think so. Some question from Sandeep. Okay, how operational research has different from the data science this week? Okay, so there are two aspects to look into this, Sandeep. So first is if you're talking about the operational research, it can be the first principle based information which is driven through the various operations which are there, which is pretty much what the functional or the engineers on the field do. But how the data science plays a part is it's purely data driven on their side. Okay, so what they do is they do some statistical calculations and help understand if parameter 1 is associated with parameter 2 which is impacting parameter 3. So it's a purely data driven approach in the data science side, and the operational side it's purely functional. And towards the end what they do is they merge these two. So now the data science folks have identified parameter 1 to 3 are the crucial ones, and they will include how functionally those parameters are impacting the health or the performance of the equipment. So it's a mixture of two, which actually helps refine the model or improve the model in terms of improving the accuracy on identifying or predicting the failures, and in the end helps the operators to take action. So it's a combination of operational plus data driven data science which is helping in identifying the event. So that's how it works. Does that help? Does that answer the question? Sure, thanks. Okay, let me move on to the oil and gas value chain part. So I would just like to cover quickly what does oil and gas value chain means. So it's a journey starting from the upstream side, which is also called as an exploration and production side of oil and gas. So this is the phase where they drill the wells, whether it be an onshore that is on land or an offshore that is deep sea, where they will go to the depths of about 10,000 feet, 20,000 feet, and identify or catch where exactly the crude oil or the natural gas reserves are there, pump it back to the surface, and do a kind of a first round of a kind of a separation. So it can be a two-phase separation which happens, which is liquid separation to the gas separation, and then sending that across to the different pipelines, or you can say the transportation. So this first phase of drilling and producing that fluid, whatever it may be, a crude or a natural gas, to the surface, and then doing a first round of separation. This sums up to be the upstream phase of in the operations, or upstream phase of the oil and gas value chain. Now we move on to the midstream phase, like I said, the transportation phase, where I'll take an example of a real life scenario. So there is a company called which is Patterson. Okay, so they do land drilling, or Transocean if they're doing an offshore drilling. So they do the drilling on the land which is owned by the operator, which can be Shell. Okay, so they are doing the drilling and they have drilled the well. Then Shell will come up and put a wellhead or whatever artificial lift if needed. So artificial lift is a kind of supporting system which helps produce the crude or the natural gas up to the surface, and they send it off to the pipelines to the midstream operators. So midstream operators are the buyers who buy these produced a crude or the natural gas, which can be Hess, for example. So these are certain players which I'm trying to map across this whole value chain. So what does Hess do is the bought crude or the natural gas, it travels miles and miles, thousands of miles, and it reaches out to their intermediate processing plants. So this is a large storage tanks kind of a facility here, where what they do is they try to separate out or refine that particular fluid even further to remove the impurities and make it pure, and which either they sell it off to the downstream operators, which are like Delek, which are like your Henkel, Honeywell, which can be your refinery owners, or your Reliance Industries in India, for example, right? So they own the refineries, or they own the gas processing plants, where they do a final level of extraction, where they produce the products like kerosene, diesel, to different chemical products like adhesives. So there are three levels of refining which happens. First is a very basic level at the upstream, then at the midstream, and then the downstream is where we receive the final products, which is either used for the vehicular purposes, transportation purposes, etc., in the service stations. So this is how this whole chain of oil and gas works out. And I've tried to map the key equipments also across these whole value chain. So starting off with the drilling phase, where we have the drop drive, mud pumps, draw works, and mud pit, etc. So there can be different equipments or the facilities which are present over there. Then if we move on to the production phase, where operators come into picture, they install separators, valves, then removing the sand, salinity, impurities, desilters, tanks, etc. So these are the different equipment which comes onto the production surface facilities for the operators. Then towards the midstream side and the downstream, I did kind of clubbed it together, where we have compressors which are high pressure compressors to push that fluid from one place to another, because like I said, it's 1,000 or more kilometer or miles long pipelines, right? So in between you will have some boosting stations or compressor stations to create that pressure differential in order to push the fluid from one place to another. Then comes the heat exchangers, heaters, etc. So in the process of distillation or any refining, right? So a certain amount of temperature has to be reached in order to separate out the constituents of the fluid itself. So heat exchanger, it can be shell and tube, fin fan, etc. And then heaters can be charge heaters, which boost the temperature from 100 degree to 300, 400, 500 degrees Celsius in order Celsius or a degree Fahrenheit, to remove the impurities and get the products that we want to achieve. So there are certain amount of temperature and pressure conditions which has to be maintained for uh, these processing units. So that is achieved by these heat exchangers. Then we have the distillation tower, where distillation is a simple process. It's you know uh, raising the temperature in order to achieve a particular boiling point, which gets separated out at different phases of the tower itself. So that's also another way where we achieve the gasoline or ethane, propane, butane. So based on the densities, it gets removed off. And we have the filters also to remove any NGL, which is known as the natural gas liquids, which are present, or you can say the heavier components, which are C6 or C7 plus. So all those components get separated out through this filters itself, and dryers to remove any water contents from that fluid itself. So I'll just try to map. There can be various other equipments also present across these equipment, but these are something which are the crucial ones, where predictive maintenance is a kind of a solution that everybody is looking. So let's try to map these here. Now let me move on to the next one, where I just try to map out what is the business objective part of the predictive maintenance. Okay, why do we want predictive maintenance? Like I said, it helps in giving a kind of a proactive alert, as in this event is going to happen, and there are few algorithms and the kind of a confidence that they bring out from that equipment itself, where they say after 1 day it's gonna fail, after 2 days it's gonna fail. So that's a kind of a time period which is levied, or which is given as an insight to the operator, so that they can plan accordingly, and they can take necessary action. For that, I mean necessary action of that engineers for that equipment. Sorry, any question? I'm sorry, was there any question here? So, like I was saying, so to take necessary actions and to get a levi time as and when it's going to fail, right? So that's a kind of an insight. But what are the business objectives which is driving these operators towards this predictive maintenance, right? So, so these points I also described a bit before itself. So to reduce the unplanned downtime. So there are few planned downtimes, which are the maintenance schedules, like I was saying, which happens after a certain amount of scheduled time period. But these unplanned ones are the ones which actually increases the operating expenditure, because these are something which is impacting their process schedules, operation, schedules, which impacts the total yield or the output that they have to serve to their customers. So what do I mean by the customers is the next phase in the oil and gas value chain where they have to sell. Okay. So these are the unplanned downtimes. Then talking about the failures, right? So there are different, time period which is needed to intervene and, check for a particular failure event. So there can be few failure events which can be, simply be intervened by a kind of a cleaning. For example, if there is a fouling which is happening in the heat exchanger, right? So there can be a methanol cleaning which actually solves the problem, which takes about a day or a two. But if you're talking about, burning of that valves itself, since the equipment like compressors are being, pushed beyond its limits, that might take few days to weeks to get that corrected and bring back to the normal operational state. Yeah, so few operators do keep a spare for these situations, but just think about, various equipment like generators, right? Big generators, which is powering the whole plant. You cannot afford to have another spare for that. So there, these identification of these failures and taking a necessary action becomes a crucial part, where you don't have a spare and you have to reduce that time to action as much as possible. So uh, you know uh, that those insights are kind of a key thing for the operators over there. Then lastly, reducing the operating expenditure and improving the utilization of the equipment. So what do I mean by utilization is, so there are various states of the equipment itself. Like for example, compressor, it can be in the shutdown phase, it can be in the transient phase, it can be in, the producing phase, or you can say the operational phase. So in a nutshell, it's an operational, non-operational, but in few that also there are few categories which are present over. So improving the utilization means pushing that equipment from the non-operational state to the operational state. Because if you are using an equipment, you would want it to work for the time period for which ideally it should be working. If it's not working, then that's a kind of a downtime, an unplanned downtime, which you have to take action on. And improving the production or the yield, because if you're a refinery owner, or managing a field, so in the field itself, there is something called as a MVC, which is a minimum volume commitment, which is signed between the operator and, the midstream company like his. Okay, so what they do is they say for a quarter or for a week also, some amount of production is what I promise you that I will, sell it to you. Like for example, if it's a big field, it can be 435 mmscfd, 500 mmscfd, etc. So these kind of a commitment is something that, it's normally shared with the midstream operators, which, Shell as an operator, right? So they have that contract with the HES. In the refineries, you have to sell that. So there is a demand of a particular product and you are producing that particular product, so you have to meet that demand itself, because if you don't meet that, then that's a, expenditure or a kind of a penalty which has to be borne by you. So these are the key business objectives in a nutshell, which is driving these operators towards the predictive maintenance. And types of the data I kind of touch base upon and try to, share it across, as in what are the operational data. So this is the kind of a time series data that I was talking about for each time step. Then maintenance data, failure logs, specification sheet, performance curve, and there's something called as an FMEA, which is, also called as the failure mode and effects analysis. So this is kind of a fault which is associated with each of the equipment. So if there is a subsystem, right? For example, if it's a compressor, so that will have different subsystems, like a cylinder of different stages. So if it's a reciprocating compressor, it can be 2-stage, 3-stage, 4-stage compressor. Then you will have a motor, you will have an oil cooler, you will have shaft and bearing as a subsystem, right? So all these subsystem based on the different events, it can lead to a failure. Okay, so all these parameters which can lead to, for example, hot valves is one such condition which happens in different stages of the compressor. In the motor we'll have a filter plugging or damage to the motor itself. So all these information about the events and various symptoms that are leading to that events itself is a kind of information which is provided by the OEM itself. So they call it as an FMEA. So there are other terms coined for this as well, like FTA, failure tree analysis, fault tree analysis. Another thing is kind of a troubleshooting guide also. So if this symptom happens, this event happens, and what should be the next best action. So all this information is also being utilized by these algorithms, ML algorithms, in order to refine and improve the predictive maintenance accuracy. I just try to map it here as in how does it look. So this is a kind of a reciprocating compressor that I was talking about. So this is a 4-stage reciprocating compressor where each bar here represent one stage. So it can be the vibration flow rate which can be captured for the compressor overall. Then if there is an oil cooler, then oil cooler will have a pressure temperature. Motor can have current, power, stator, bearing, winding temperatures, and for each stage you will have a suction discharge pressure, suction discharge temperatures, intercooler temperatures, etc. So see, all the equipments will not have all the information captured as a part of a time series data, right? But there is a bare minimum parameters which has to be present there. So it will be the sensors which are installed over the equipment which is capturing these parameters. Okay, so for the motor, for example, current and the temperature are the key things which has to be present. Anything on top of it is actually help improving the models, but there should be a bare minimum which has to be present in order to check the feasibility as in how these predictive maintenance as a solution can be created for the equipment itself. Then this is a kind of a performance curve for the compressor. Like I was talking about, you will have a head or total head and the volume, and based on that, on the different efficiencies, how that particular you know the flow has to be moved according to that total head itself. So this is a kind of a performance curve that ideally it should follow. Any deviation from it is kind of an insight, as in it's not performing optimally the particular equipment. And this is a kind of a maintenance log. So whenever it's going for a maintenance, so there is a kind of a checklist which happens for each of the items here. So this checklist also helps them identify, okay, what are the different issues that were identified and the actions taken in the scheduled maintenance. But there is a separate failure logs also which happens between that operational time of that equipment. So this is in a nutshell different data sets or the information which is captured for that equipment itself. Now, lastly, I just wanted to touch base upon how this modeling approach, happens. So I just covered everything in bits and pieces here and there, but let me just try to put it in one workflow. Okay. So first is whenever an equipment is selected for the predictive maintenance, right? So the first check is what is the data sets or the information made available. So does it have a static information and the dynamic information like time series data? If it's there, what are the different parameters which are there? So if 3 parameters bare minimum has to be there so as to derive any features. So what do we mean by features are these are the calculated KPIs, you can say, which is not captured directly by any sensor or anything, but has a whole lot of an impact, or you can say insights can be driven for the performance of the equipment. For example, if there is a pump, okay, so pump, there are various sensors present like flow rate and the pressure. Okay, now if I have to get onto the performance of the pump, I need one metric that will help me understand whether the pump is operating optimally, or it is underutilized, or if it's overutilized. So overutilized means above that optimal range it's being pushed. Underutilized means it's not even going to that optimal limits. It's very low flow rate is flowing for that particular pressure, for example. Okay, both this under and overutilization will have an impact on the performance of the equipment, and in turn might lead to a failure event. Like underutilization might lead to cavitation, etc. Then overutilization might lead to overheating, which might cause some downtime. Okay, so I need some metric to gauge the performance. So what I'll do is I'll go ahead and calculate one feature which is called as a percentage of BEP. Okay. So BEP is called the best efficiency point. So this is the point in the performance curve for that equipment where for a total head and the flow rate for that impeller diameter, this should be the flow rate ideally I should be flowing. But with the current flow rate, which I'm capturing from the time period, I'll take a ratio of that with the ideal flow rate, which is at the flow rate at the BEP, that is best efficiency point. The ratio of that will actually lead to a percentage of BEP. Okay, that will help me understand, and I'll put a kind of an optimal range for that. For example, 70 to 120% or 50% to 150%. If it's less than 50%, then that means it's being underutilized. If it's greater than 150%, it means if it is overutilized. So this is a kind of a metric that can be derived. Similarly, for compressors, it can be a compression efficiency, where we can take the ratio of different stages all across, or overall the discharge pressure by the suction pressure, and we can take a compression ratio of that. And for that efficiency, if it's an isentropic, there are certain formulas for that. If it's a polytropic, there are certain formulas for that. So using that, we can calculate these efficiencies. So all these calculations is a kind of a feature engineering that we do. So this is purely on that functional side. Now talking about the data driven side, like the data scientists use. So it's a window based or a time based features which is created. Like I'm pretty sure you must have seen in the statistics, like there is a 90% quartile, 10% quartile, the mean, median, mode. So we take a kind of a time period or a time window, like 1 hour, 2 hour. On 1 hour, 2 hour, all the data points which is there, what is this metrics which is being captured. So these metrics itself can be used as a feature which might give some insights of the behavior of that equipment itself. So this is called as the feature engineering here. But from reaching the feasibility to the features, so now we have identified what are the raw parameters which are available and the features which can be created. Before that, there has to be some cleaning which needs to happen, because in the extreme conditions of the field or the high temperature pressure conditions of the plant, the data which is normally consumed or the captured ones, it's not ideal. As in, if the temperature should range between 100 to 200 degree Fahrenheit, it might shoot up to some trash values, or it can throw off some values which is not even possible. So that is something which is called as a noise in the data. So what normally the data scientists do is they clean the data. So they do, okay, ideally, what should be the optimal ranges and what is the possible optimal ranges. So you cannot expect the pressure to be 1 lakh PSI, right? So there are certain ranges that is possible for that process itself. So we'll clean the data and impute the data. So what does data imputation means? There are few chances or the possibilities where the data might be missing out in between. So it might be the sensor error, or the equipment itself was wasn't running optimally, so that data points got missed. Okay, so all these data in between has to be imputed, because there are two ways of approaching this. First is we can ignore that data itself, but if we are lacking the depth of the data and we have to use that data, what we do is we impute the data. It can be a forward fill or a backward fill, or imputing with the mean, or imputing with the zero, so or with a static value. So that is some data treatment which has to be taken care, which based upon different parameters and the data ranges, etc. So this sanity check and the treatment has to be done on the data, and then the features are developed on top of it. So this is for the predictive maintenance or the prediction perspective. But if you want to analyze it in real time, as in if there are any signature which is going haywire, okay. So this is something called as a diagnostics part of the analysis, or we can call it as an anomaly detection as well, where some erroneous behavior is identified. So if the flow rate should be stagnant, but if in between there we see some spikes, or we see some sinusoidal curves, for example. So these are certain indications of an event like cavitation, etc. So all these events are captured as the anomalies, for which also there are some ML models which can be developed, like a Bayesian change point, which is a kind of a trend-based anomaly detection module, and other algorithms as well to identify these spikes. So this will not help predict the model, but more in terms of it will help identify if there are any signatures which is happening in real time. Okay, so that's also kind of an alert which can be generated and sent out to the reliability engineer folks. Now, moving on to those features. So what they do is now they train the model. So what do we mean by training the model is they seize the historical behavior of the data. So the crucial aspect for the prediction modeling is we need to have a good amount of a failure data. And if you're going, so there are two approaches for it as well. So there's a supervised learning and unsupervised learning. I know I'm bombarding with a good amount of some industry-based terms here, but probably you can go ahead and search for it in any search engine. So supervised learning means we already know these are the kind of signature or behavior which is identified for the equipment itself, and we already know this is how the behavior is going to be based on the experience or any of the previous process flows. So we train the model or help the model see if these are the behaviors that if it happens again, give me this as the failure event. This is the supervised learning approach. Second is an unsupervised, where we are not even aware what is happening. So this is the first time I'm saying I'm not aware of any signatures. I leave it to the model. First, give me some insights. Okay, does it lead to any event, or what could be the possible reasons? So that will help identify, okay, some behavior is identified, some signatures are seen in the trends which might lead to a failure event. So that's a kind of an unsupervised learning approach which is present for any of the event. So there are different algorithms also present for each of these kind of a learning methods. So supervised also will have random forest or decision trees, so some predictive models which are available. For non or unsupervised learning, there can be SVMs, etc. So these algorithms are then chosen. These features are seen which has a good correlation with that event, whether it be a regression model or a classification model, and then a model is built and the failure is predicted. So now the model sees, okay, in the past this behavior happened, this event happened. Again, if that happens, then this is the probability, okay, this event might be happening, because simultaneously one or more events can also be present, right? So for each of the event, it will give a kind of a probability of this failure is going to happen. So this is how a prediction model is built. So there are other things as well, like if you want to scale up the model, if there are new sensors or measurements are being captured, or if there is a new failure event which was seen, or if you want to scale this across different type of equipment, so we have to kind of work around or retrain the model, where we introduce new features, we improve the different KPIs or the features which have to be included into the training itself. And then again, this whole workflow is run in order to refine or update that model. So this is something which is called as a model scalability or model retraining, which is also one other process which happens for this modeling approach itself. So this was about the modeling perspective and how, so first is what we covered was what is predictive maintenance, why is predictive maintenance needed, and how is predictive maintenance done. So I just tried to cover all these 3-4 buckets in this quick presentation. So this is kind of what I had for today, since it was a short and a first level of introduction towards this itself. But feel free to let me know if there are any questions, or I think so we are a bit over time also. So if you want, you can connect with me over the LinkedIn. Probably I'll share my number with Nitish or the Advantage, and they can share it with you. So you can reach out to me if there are any questions or any doubts or any feedback or any thoughts that you have. So we can have a conversation on that as well. But from my side, I had this for today. Yeah, thanks. So anything?